Okay, welcome back for rule number 3. I think rule number 3 is going to be my hardest sell for you because units can be a gifted kids. It's like the second worst thing to show your work, right? I mean, show your work is the worst. Do show your work. Oh my goodness, show your work. But it's really hard on us, for a lot of us gifted kids. And then, yes, I am a 47-year-old gifted kid, but working with units can be really, really frustrating. And I was lucky enough to have, kind of like Zara's mom, my middle school science teacher was a scientist who was taking time to be mostly a mom. Right, so she was teaching at the school that I went to, and she was doing so because her daughter went there, and she was not being a full-time scientist at the time, but she taught us as if she was teaching future scientists. So she was hard on us for certain things. It was a fantastic class, but oh my goodness, she was hard on us for certain things. And one of her main things that she was hard on us and seemed really unfair at the time was units. So let's say we had a blank on a test, right? And the question was something about a volume that we were supposed to measure, right? And you had to put in the answer for the volume. Well, let's say I used all my proper lab procedure and I found the volume she was looking for and the answer was 10, right? This would have gotten me 0 credit, 100% wrong, even if all I was missing was the units. Even if all I was missing was the units, because she said, if you haven't told me the units, you haven't told me anything about what I've asked you for. Units are really important. And we're going to see in this class that units will absolutely help you. Towards the end of this class, you will be deriving something called the wave equation, and it's going to have trigonometry in it, and it's going to have lots of interesting stuff in it. And step by step, you will derive the wave equation. And when you do, we will move our units around, and by the fact that we check that the units are right, we're going to figure out that our wave equation is in fact correct. We're also going to find new versions of energy. We're going to transfer one kind of energy to another kind of energy, and we're going to check our units. And as long as our units for energy work out, we will know that we have in fact successfully transformed one form of energy to another form of energy. These units are going to be really important. Now let's look at something. Force, when I said in class was the definition for force is kind of a, I don't know, because it really was an I don't know. We talk in the Newton Leads the Way class and later in this class when we get to energy. In fact, in a couple of weeks, we're going to repeat an experiment that Leibniz and Émilie du Châtelet did to prove to Newton that energy was something different than momentum and than force. And in all of that, this was new stuff that nobody had ever encountered before. Now we can say we feel a force, we feel the force due to gravity pulling us to the earth, we feel a force when we're moving around in a car, so we have a sense that it exists, that it's a real thing, but what is it? Well, we're lucky because we have found over time, with lots of experiment and checking, that this equation, which is one of Newton's laws of motion, force is equal to mass times acceleration, turns out to be true. That's a terrible A. My Wacom board isn't working today, so it's a little bit hard on me. Okay, so force is equal to mass times acceleration turns out to be true. For this I don't know thing of what is force, we can figure that out by looking at the units of mass and acceleration. So let's say I want to find the force due to gravity. I put a little g right here to say what kind of force is this? Oh, it's the force due to gravity. We want to find the force due to gravity of a 5 kilogram weight. That is, let's say I'm going to drop a 5 kilogram weight and I want to see what using the force due to gravity, what is the force due to gravity that's going to pull on that 5 kilogram weight? So my mass is going to be 5, and it's not just 5, it's 5 kilograms. So let me put my little kg there. Okay, now acceleration is going to be harder. I will tell you, and this is something you can find, if we didn't really cover it in the Newton class, it is in the Newton book, but I can help you figure out how this acceleration was found. And if you're super motivated, there is an experiment you can do with some bricks, a ladder, and a tuna can that will help you see how this was calculated. But the acceleration due to gravity is 9 on Earth, is on average 9.8 meters per second squared. Okay, well that's already weird in itself. Well, let's look at that. So in class, I said that acceleration is equal to any change, and somebody mentioned the sign delta. We do have this sign delta that we use to mean change. So we're talking about the number part of the change. It's going to be this delta. That is the change in velocity. So acceleration is equal to change in velocity. Okay. Velocity is calculated. First, change happens over time. So if I'm going to do, so the delta is the number part. This is the acceleration is equal to the change in velocity over time, because there's no such thing as a change which doesn't happen over time, unless you count. We'll talk more about that, but it's the change in velocity over time for acceleration. Maybe I should say that more because of where we're going with time travel, but acceleration is the change in velocity over time. Now, what are the units of velocity? Well, we talked in class that velocity is speed plus direction. We're not going to talk about the direction part of velocity at this part. We're just going to talk about the number part. When I'm talking about the direction part and the number part, you put a little arrow hat on the top of it. This is just the number part right now, but we're going to remember that there is a little direction part in a little bit. Okay, so velocity is equal to distance over time. So that would be miles per hour, meters per second, those types of things. So I can replace the units for velocity with distance over time. So the delta part, the delta is now going to be my number part of this change, whatever that change is. And it's going to happen over time. And it's going to be what the units are going to be in some kind of units of distance over time. So the unit we use for distance in the SI system are meters, and the units we use for time is seconds. So the units are going to be seconds and meters over second. Okay? So our units, so we're going to have some number, and it's going to have, these are the units. Now, when we have this on top, that's the same as multiplying. So we multiply and divide. I can move that divide down to the bottom. So what happens with that is now I'm left with an M on top, and I move the S down, and so it's S times S when you move it down. Okay, so that's why the units for acceleration are, so this is the number, the delta is going to be the number part, meters per second squared. So over here, the acceleration due to gravity is going to be 9.8 meters per second squared. Okay. When I do this, my force due to gravity, get my calculator, and yes, you can use a calculator in my class if your parents allow it, but you should probably always use a calculator. 5 times 9.8 will equal 49. But 49 watts? What 49 do we have? 49 kilogram meters per second squared. Wow. So it's 49 kilogram meters per second squared. Now what is a kilogram meter per second squared? Well, it's kind of like if you had to point to one, you couldn't see one, right? Because you can't see a force, so you can't see a kilogram meter per second squared. But force is measured in SI units. Force is measured in how much force it would take to accelerate 1 kilogram a meter per second. That's how we measure force. Okay, let me show you a little bit more about rule number 3, which is what you can do to numbers, you can do to units. So if I am taking the square root of something and it is 8 seconds squared, let me just choose something that's easier. 9 seconds squared. The answer to that is not plus or minus 3, but that's a good start. We have to take the square root of the s squared. So the answer to that is plus or minus 3 seconds. Likewise, we're going to square distance a lot. When I'm squaring a distance, let's say the distance between two things is 5 meters. I have to square the whole thing. Okay? And when I square the whole thing, I do not get 25 meters. If you tell me that the square of that is 25 meters, I will have to count you wrong. The square of that is 25 meters squared. Okay, I had to cut off the last part to make things make a little bit more sense on this side. So we ended with the square of 5 meters is not 25 meters, it's 25 meters squared. So let's take a look at a little bit more of how this works when I have equations and I'm trying to do the same things to both sides of the equation. So let's say I had some formula, and I'm going to use our don't look down technique. And I'm going to say there's a big bunch of formula over here. Okay, and then on that side of the equation, I have times 3 meters, right? Times 3 meters. And on the other side of the equation, I have, we just talked about force as being kilogram meters per second squared. So let's say on the other side of the equation, I have 27 kilogram meters per second squared. Now, I want to solve for blue. And what blue is, I don't know, because I don't know of anything that's going to end up in units of kilograms per second squared. But let's say this magical blue thing is going to show up on that. What I want to do is I want to get blue all by itself. So I'm going to divide both sides by 3 meters. Divide both sides not just by 3, but by 3 meters. So over here, this already has a fraction bar, so I'm just going to add 3 meters underneath the fraction part over here. Put a little dot to remember that's a times. Okay, on the left-hand side, 3 meters over 3 meters, 3 over 3 is 1, and meter over meter is 1. So the 3 over 3 cancels, and the meter over meter also cancels because that's a 1. That's just like multiplying it by 1. And I'm left with where's my box thing? I'm left with the big blue box by itself, which is what I wanted. And on this side, I have kilograms. Well, there's nothing underneath. I have meters over meters because times you get to act like everything's over each other. So meters over meters is 1, so I get to take that out. 27 over 3, I get to put the 9 here and get rid of the 3. I'm left with 9 kilograms per second squared. I got rid of the 3 that was on the other side, but with it, something happened to my units over here. This is the big deal about this. This is the very big deal about this is that the units will cancel out. They'll move over with the numbers and they'll cancel out and it will change what you're solving for. Because where we had force here before, we now have something new, which is kilograms per second squared.